Okay, good. What are we working on these days? Small oscillations with many degrees of freedom. Many is any number at all, but many is also just 2. Because those are the ones we can really calculate. So we had been working on this thing. I thought I'd just demonstrate it again. We have a few other things in store for us. So this was made in the house here. I'm going to go ahead and put the spring on the middle. This thing is a realization of the 2 connected pendula that Thomas calculated last Friday. So and so we just got the Lagrangian. Did we get those 2 frequencies also? I think we did, right?
Yeah.
So we got the 2 frequencies, and the one of them is that these things are swinging without involving the spring. And then those are just literally the 2 same frequencies of each individual pendulum. The second one had the 2K prime, or the 2K added to the georel, right? And that one was this mode, as it's called. Okay. So it's being pulled and pushed a little bit, and consequently it has a slightly higher frequency. Not enough for us to actually tell just by counting it out, but this frequency, what was it, omega squared? What do we have here? So since we did this last time, now I'm demonstrating it in real life. My example has the spring in the middle. In fact, it's adjustable. But the one we calculated last time had the spring right there. Phi1, Phi2, L, M. And what we had was, I'm just going to say omega 1 squared was G over L, omega 2 squared, G over L, plus, what was it, 2, you have that one there, Thomas?
It was 2K over M plus G over L, I think.
2K over M. Makes sense, right? This one here would actually be more complicated, it would involve the L, but we don't care. The point is that this one is slightly larger than the first one, and we can control it by making K as small as we need. So that's the way to look at this one. Good. So yeah, once again, G over L is just a classic pendulum, and then G over L plus a little is with the spring. Okay. So one of the phenomena, we're going to calculate this thing thoroughly, is that if you start this thing with one, so everything's at rest, so initial positions, this one is pulled forward, this one is at rest in this equilibrium position. Velocities are 0, we release from rest and wait a little bit. And there you go, now they're both involved. But what happens is this first one will come to a dead stop for an instant. And now this one has all the energy of the system. And now it's going to keep going, and the first one will return to its initial dead stop. This one right here, and then that one's moving. So that's something we're going to do mathematically. That's a really important calculation and phenomenon. What we're doing is beats, and the frequency with which the energy goes from one to the other is the beat frequency. Now I brought something else. We'll just go ahead and put this here. Has anybody seen this thing in action? This one's really interesting. it also has two coupled modes. Vertically, it's just a mass on the spring. Get a little more elevation here. Here we go. So vertically, we just have. Go. Okay, now once more. Okay, it's just a mass on a spring, but you'll notice the spring can be twisted. So it does what are called torsional oscillations. We should probably do a little torsional oscillations as well. Okay, so it can do both of those. And the thing is, this thing has been tuned with the addition of these little masses on the outside. It's been tuned so that these two frequencies are very close to each other. So watch what happens. What will happen is the vertical coupled to the torsional oscillation, and this thing's going to come to a dead stop vertically at about this instant now, and then it's going to continue on and go back to vertical oscillations. A little too much damping for this to happen many times, but you see you're getting the same phenomenon as you do there. So I can start this one just purely torsionally. Thing is, you get some serious torsional oscillation. Now they're going to stop twisting entirely for an instant. They'll just be moving up and down. Those are the coupled oscillations. Okay, not bad. And that's what we're working on in class here. So one of our goals is to do the calculation. This demonstrates this. And we'll get to that. But yeah, I wanted to make sure we see these phenomena. So yeah, let's call this demo coupled oscillations. So maybe we'll do that calculation today since it's on the table. Both of these here. And actually, let's put up here example. The one we're going to actually calculate when we get around to it is the three masses and two springs. So we have locked off here with no friction, equal masses, equal springs out here, a different spring in between. Now this is the one I did in class, right? Did I do this one pretty thoroughly? And this one we had done yesterday not yesterday, on Friday pretty thoroughly. One of the first lessons we have to get is to see the equivalence of these two small oscillation Lagrangians. So I'm going to put this as a node. Equivalence of Lagrangians. This is a really important lesson. So let's say we had here for this guy, okay. Little mock-up. So the Lagrangian for this one had this form, L 1/2 M x1 dot squared M x2 dot squared minus, and I'll bracket there, 1/2 k plus k prime minus 1/2 k prime x1, x2 I'm writing it out like that, then this is a standard form. And then those two matrices, we had M, 0, 0, M. And for this matrix here, we had K plus K prime minus K prime minus K prime, K plus K prime. Okay, so we had done this one, and actually, let's go ahead and, I want to have this all on one. So we had omega 1 was root K over M. Omega 2 was root K plus K prime over M. Sorry, K plus 2K prime, right? Over M. Good. And we're going to continue working with this system, but the realization of this system here in the classroom is this system. Okay. And that's what I have to prove to you guys, what we have to just convince ourselves of. So the other one is this here. Okay. So this system here. Now what was the small oscillations around you? It was 1/2 ML squared V1 dot squared. 1/2 2 dot squared. And you guys help me out with this. We had 1/2 G over L plus 2K over M. Is that what we had there, Thomas? We had it all, oh, P1, sorry, P1 squared. Plus, I'm going to do a little trick here, minus was it 2K over M or K over M? It was 2K over M. 2K over M, P1, P2, minus, or plus, negative 2K over M, P2, P1, plus 1/2. Immortalize this. Is that what we had there?
No, I don't think so.
What do we have?
We had KL squared plus MGL times theta 1. Because you don't get the 2K over M and all that until you do the matrix
Okay.
of omega squared.
So remind me what we had. We had K. What do we have here? What did we have for this first one?
We had KL squared plus MGL times theta 1 squared.
Okay, gotcha. I'm going to write MGL plus KL squared P1 squared. Good, yeah, I was cutting to the chase, wasn't I?
Yes.
And then what did we have here
Same thing.
without the MGL?
KL squared plus MGL theta 2 squared.
That was this one. I'm doing a different order, okay, it's fine. So, KL squared plus MGL B2 squared.
Then yes, KL squared or theta 1 theta 2.
Okay, good, thanks. Yeah, I knew I wanted that, and this had a minus sign.
I think it was minus Q.
KL squared B2, B1. This is if we distribute them. There were two of them, but then they come out like this. Good. We got that? Thanks. Okay, fantastic. So now let's get this matrix. And you probably had that on the board then too. Mij, this time it's ML squared ML squared. Kij, important to get this right, MGL plus KL squared minus KL squared. Yeah, that makes total sense. Minus KL squared. MGL plus KL squared. And the frequencies here, omega 1 was root G over L, and omega 2 G over L plus 2K over M. Good, that's perfect. Now it's all up on the board in one grand diffusion. The point is that these Lagrange, at the level of Lagrangian, we can already see that these two systems are equivalent. Because we just have to rename things. For example, if we rename ML squared to M, it'll be the same. And then if we rename, MGL to K and KL squared to K prime, they're the same. But those are just renaming things, right? They'll have the same form. And this is really important because if we solve this system, we inherit the physics for this system and vice versa. So we don't have to solve them twice. So we solve this, and we could actually rename these things, plug them into here, and this is what will come out. This is just a generalization of the fact that when you're doing small oscillations, it doesn't matter what the name of your dynamical variables are, right? It's just a cosine omega t when it boils right down to it. So let's see that in action. So omega 1 would be the square root of K over M. So the K would be MGL, and the M would be ML squared, which of course is root G over L, just by renaming. And then the omega 2 would be the square root of the K plus K prime, which would be MGL plus KL squared over the M, which we just renamed to ML squared. And then we get what we had there. So the G over L, and then the K over M. Where's the 2 come from? K. Oh, forgot the 2K prime, right? 2 K over M. So yeah, just by renaming them. So that's, referred to as mapping one Lagrangian onto the other. Right? This is different, this is linear, this is angular, different. Good. So let's put some words behind this and then make sure that you see. I'll go ahead and erase this, get a little room here. So important to note, the two Lagrangians are equivalent. However, originally this one was not equivalent. It was equivalent when we did the small oscillations. Originally this one had, nonlinear functions and stuff. So our equivalent at the bells of small oscillations level, and then we just inherit the results from one by renaming things. that's really important to understand. Hey, maybe I should do that calculation now. So the homework, of course, for this Friday is that double pendulum. Was there anything else yet?
No, you just signed that problem up because it's really complicated.
It's a good one, right? We'll just do it really systematically. And, you know, I ask you to get the Lagrangian, then we'll get the small oscillation Lagrangian, and we'll take it all the way through. And then we'll inspect it to see if it will have this beat frequency phenomenon as well. At which point Sam's going to show us his computer programs, right? Which are pretty interesting for the double pendulum. So that'll work out nice. Yeah, I think I'm going to start on and probably be able to finish the calculation that demonstrates these beat frequencies. So we're going to be working with this one up here because the formulas are a little simpler. So we see the equivalence. Actually, there are a couple more steps before we get there. So either today or today and Wednesday. So if we go ahead and fix the report. Okay, so returning to two masses and three strings. This is really the key to a lot of interesting stuff. X-axis, X1, X2. Now we ended up with, we had determinant negative omega squared m, I'll write ij to show that it's a matrix, plus kij equals 0, which gave us omega 1 and omega 2. The step before this, we had this from negative omega squared m plus k vector a equals 0. If you remember that, we had that from the equation of motion. That looked like sum over negative omega squared mij plus kij aj equals 0. So this was j equals 1 to n. Remember we worked our way through from the equations of motion, matrix equation, and then the condition on the characteristic polynomial. And this was for I equals 1 to n. Of course we had 2 by 2 matrices, but this was the general calculation. And before that we had, so this is from this, before that we had let xj equal a sub j e to the I omega t, which was our general solution, our trial solution. So yeah, there's a little linear algebra here that we did. And I had pointed out we have to do this, we just did this once and for all. And then what we did now more recently is we just found these two matrices. And they were second derivative. This was the mass and this was the second derivative. Good. So that was the progression there. And also recall that Mij was Aij of Q0 0. At equilibrium, Kij was d squared u dqi dqj at equilibrium. So there's the complete recipe for this whole program. Well, this has to be discussed a little more. Because we can, we didn't bother finding these eigenvectors. The vectors A are eigenvectors. Eigenvectors to the eigenfrequencies omega. So we'll just say A sub L frequencies omega sub L. And there are up to n of them, n linearly independent eigenvectors. So the general solution to this differential equation is a linear combination. This is a linear differential equation. The general solution of our differential equation looks like this. X of t equals sum over alpha sub L A sub L e to the I omega sub L t L equals 1 to n using L for unit x. So that's the general solution from linear algebra and from linear differential equations. That could be pretty complicated. And what we do is we have, well, since these are vectors, right? We can do this. x1 to xn of t. So alpha sub 1 vector A sub 1. So we're going to have a matrix. We'll have, actually no, let's not do this yet. Matrix. We will have alpha sub 1, A sub 1, 1, A sub n 1, e to the I omega 1 t, plus all the way here, alpha sub n, A sub 1, n, down to A sub n, so that's the general solution. And these alphas of L are complex numbers. So this analysis we did with this thing here, this device here, or with these two masses, we were already looking at these two simplified motions, the one where they're together and the one where they're doing this. This isn't showing us that. Actually, this is since x1 and x2, x1 would be something e to the I omega 1 plus something else e to the I omega 2. But these are eigenvectors. And so this structure actually does have some way to simplify it. You'll notice that I took the eigenvectors as column vectors. So that the label on the eigenvector 1, 2, 3 is in the column. In the column, eigenvectors are columns here. And this does turn into a matrix equation if we look at it closely. I'm gonna erase the left side here. Keep this mock-up up there as a reminder. Because I'm going to put I'm going to put this as an important homework assignment. So homework. So for this system here, show that A1 equals 1, 1, or omega 1 equals root K over M. So I'll put an arrow here, and A2 equals 1 minus 1. We don't have to normalize these vectors, okay? 1 minus 1, or omega 2 equals root K plus 2K prime over M. Yeah, really crucial. Really crucial. And you can see the meaning of these eigenvectors right here. 1, 1 means I'm moving together, okay? And that's the frequency where the middle spring is not playing a role, okay? 1 minus 1 means I'm moving against each other. And that's for that frequency. So you're actually going to go into these matrix equations minus omega squared M plus K times A equals 0. So you're going to turn that into a matrix. Remember, the omega is either the one or the other, this or this, and they're trivial. They're very simple eigenvectors to find, but you definitely want to get both of these. So when you return to this problem, set it up far enough in advance so you see the whole thing. Get these two eigenvectors with the corresponding eigenvalues. And then I'm going to take those results into here and work with them. Okay. That's the plan. Because this is the n-dimensional version, or the n degrees of freedom. We have 2 degrees of freedom. We can knock this thing out completely. And if we don't finish it today, we'll finish it on Wednesday. It's pretty good one. So yeah, get those eigenvectors and eigenvalues. And that's a good chance for you to just go back on this thing and pick from the top. Okay? So you can actually take this whole problem from the top and see that. And now I'm going to write this down in terms of those eigenvalues. So for our system here, so having done that, we now have x1, x2. Took among vectors much nicer, right? That's what we work with. We have alpha 1, 1, 1, e to the I omega 1 t plus alpha 2, 1 minus 1 e to the I omega 2 t. And we have to turn this into a real solution. Okay? We have to take real parts of all this. So these are complex. And therefore we can say this is 1, 1 e to the magnitude of alpha 1 e to the I omega 1 plus, I gotta use some other letter here. Omega 1 t plus b1, okay, plus 1 minus 1 magnitude. So this is what we learned last semester with complex numbers. Alpha 2 e to the I omega 2 plus b2. And of course, let's see here. If we wanted the real part of this, cosine omega t plus phi1. And then, because we have a magnitude cosine omega t plus phi1, we can turn that into a cos omega 1t plus b sine omega 1t. 2 steps downstream, right? We can do that. The intermediate step, of course, is alpha 1 cos omega 1t plus b1. And then we expand that out, we get the cosine and sine. So yeah, that we can do here. And we can do the same thing here. So we can call this b cos omega 2t. No, c plus b. C cos omega 2t plus d sine omega 2t. So I'm going to write down what we now have, and you'll see this eigenvector structure plays a big role. So these things in red are, like I said, what this gave us. We'll erase this. And put that picture up there. So now what we're doing is solving we have x1 p equals a cos omega 1t plus b sine omega 1t. That's the first one. And see, notice we have a 1 up here as well, plus c cos omega 2t plus d sine omega 2t. And when we do the x2, because of the relation they have, it is eigenvectors. It'll be the same thing here at a minus sign in front of that one, or minus 1. And all we have to know right now is that omega 1 is less than omega 2. Which we had. Omega 2 had 2k prime and 2. Okay, you know what? I'm not going to be able to finish this today, but that's all right. Let's just describe what we're going to do here. And, so we're trying to solve this with initial conditions. And the initial conditions are the ones I did with the pendulum. So I'm going to let x1 be held out somewhere and everything else at rest. Okay. So initial conditions. Initial conditions are x1 t equals 0, x1 0, x2 of 0 is equal to 0. But we didn't hold that one. Right? We only held the one pendulum out. And then x1 dot of 0 is going to be 0 because it was at rest, and x2 dot of 0 is 0 because it was at rest. And these 4 equations will allow us to specify these 4 constants, and then we'll have our solution. 5 minutes, race against time, I don't know. We're in no hurry. We're in no hurry. Let's see what happens for a couple of these. We'll save the punchline for next time. It's going to be a little discussion. Yeah, I'll put this up next time, but let's just get started. So we have this first condition here. So we have x1 0 equals a. T equals 0, there's a 0, there's a 0. So x1 0 equals a plus c. And the second equation The other two take a little more work, so x1 dot is equal to minus omega 1a sine plus omega 1b cos omega 1t minus omega 2c sine omega 2t plus omega 2b cos omega 2t. And then we put the 0 in on this one, we get 0, so we get omega 1d plus omega 2d. And for x2 dot, yeah, we're really gonna get the punchline on Wednesday. For x2 dot, we have negative omega 1a sine omega 1t plus omega 1t cos omega 1t. We're just switching signs on these, as you can see, so plus omega 2c sine omega 2t minus omega 2d cos omega 2t. We plug the zeros in and we get omega 1d minus omega 2d.
They're both equal to 0.
Exactly. And that's what we're going to end the hour on. So these two equations, you add them once, you subtract them the other time, and you can conclude that omega, no, not omega, b equals d equals 0. Oh, good. So anyway, that's how that's done. And next time we'll actually start with this, set this up again, and then get some really interesting results on this general solution. Because we have the initial conditions, we haven't, other than that, we haven't made any approximations. So we'll have an exact solution, get some interesting results. Okay, good.